Thank you very much. This talk, it's a collaboration between three organizations, CSIRO, Geological Survey, and QUT. Before I begin, I sort of acknowledge all the authors, that's Nathan Reed, Rob Thorne, Cleo Platt, and Tim Pinchard from CSIRO, myself, Dominic Brown, and Dave Purdy from GSQ, and Bas Campbell from QUT. I also like to thank all the property owners who has granted us permission to sample their bores, and also companies. And I saw some of you here that really assisted us, especially El Luis from South 32, Kennington, Glencoe in Ennis Henry, also Dougal River and Copper Mountain. Thank you very much.
If you're inside there,
yep.
And you just go.
Oh, okay. Thanks. For this talk, it covers, I'll sort of narrow it down. There's two things that I'm going to narrow down. Firstly, I'll get rid of all the maths, all the calculations, and just give you pictures. I know the geologists don't like, the numbers, so we'll concentrate on that. Secondly, I think it's a big question that a lot of people ask is that, how different is hydrogeochemistry from conventional chemistry? And that's something that I will explain from the planning, from designing, from data processing itself. And then I'll sort of step into the data, basically on data processing, how to use hydrogeochemistry, and the importance of appending your data to regional geochemistry to get a trend, and sort of sum it up with economic and environmental significance. Well, from the talk yesterday, from the toolkits, we did stress that, in certain exploration domain, that's the deep ones undercover, or the ones under, blind deposits, hydrogeochemistry is really pivotal, for finding old deposits. That's because most geochemistry would not reach the surface in those, areas under deep cover. Basically, you could take boreholes as probe into the subterranean. It reaches places where geochemistry can't come out or can't reach. Hydrogeochemistry or ground water interacts over a period of time with long residence time with the chemistry of the water itself generally reflects strongly on the alteration, on the sort of mineralization or whatever process it is. And you could use these to decipher, alterations and mineralization underground. CSIRO did a lot of pioneering study led by the late David Gray. And basically what they've done is they look at, the borehole spacing, look at methodology, etc. And they come to the conclusion that sampling between 10 to about 5 kilometers, and some put it up into about 10 kilometers, would give you sufficient geochemistry to decipher what's underground at depth, or the chemistry at depth itself. The one thing that I will stress at this point is that geochemistry is very different from conventional chemistry. For a start, it's not a fixed entity. Unlike a rock chip chemistry, you could analyze it for multiple times and give you very similar results. Water chemistry, you can't do that because it varies. It varies with the amount of recharge, the amount of discharge, the amount of water mixing itself. And also in situ itself, it can change with changes in pH, with oxidation level, with temperature, basically it changes with season as well. The other thing about hydrochemistry is when you use it, you got to remember there is no physical dimension to it. The boundaries is flexible. It changes with season. It changes with the amount of mixing or amount of, backflows from the well, etc. And so it is really different from conventional chemistry. The next thing is, how do you plan a hydrogeochemical program? We'll talk about how useful it is first, but before we get into that, we'll talk about how do you plan. Basically, there are two data sets that you have to visit. The first one is the CSIRO Geochemistry database. It's a database that the Geological Survey has contributed or helped to sort of build this up. and it goes through a central depository. The reason for that is they had to know how to correct it, to check it for contamination, etc., and what's good data and what's a bad data. So we sort of let them do the hard work. The second one is the Queensland Borehole Register. This register basically, ideally should register every borehole drilled in Queensland. The only problem with that is that it's not been updated, and so the locations might be a bit dodgy. Nonetheless, it gives you two things. One, chemistry, a chemistry that you could append your study against a backdrop of chemistry to look at the regional trend. The second thing is that it gives you the locations of those boreholes. Some of these, like for example, CSIRO might just give you, has a chemistry and a location, and it has a sort of data that's not in the borehole register itself. And therefore, if you combine the two, it gives you lots of areas, lots of sort of, boreholes or locations you could take chemistry from. Next, we move into the ISSA project itself. This project purposely picks those, it's undertaken on the eastern margin of the Mount ISSA project. We try and sort of, work on the domain 2, the domain 3 and domain 4 areas of that, but also includes the Mary Kathleen, sort of domain, part of that as well. There are two areas of this study. The northern ones goes from McKinley to Kamilaroi and covers about 10,000 square kilometers. This is a well-organized, well-planned program. The southern area, it's in and around Kennington. It's what I call an opportunistic, sort of campaign, because we work closely with South 32, and so they allow us to their boreholes, the farm bores, etc. And so we sort of take the opportunity of that. In between the two of that, we sampled about 302 boreholes. What do you sample? Basically, the water that you are interested in is the saturated water, water that has resided and in equilibrium with the rocks over a period of time. That's the where the water below the water table itself. The next thing is that before you start a campaign, you need to do a lot of planning. The first planning is to look at the suitable borehole. For the area that we are interested, there are about 800 water bores that's available. And we went through and cull, and I'll use the word cull, wells that's not suitable. Basically, if the well is open all the way from bottom to up, you start collecting water from, generally from the top profile rather than the bottom profile. The ones that you want are wells that's open at the bottom or it's screened at the bottom. So these are the wells, and we filter down to less than 400 bores that fits that criteria. The philosophy, very simple. When you draw from a well, you create a drawdown cone around that well. With that drawdown, it creates a negative pressure, in that area, and so it drags all the formation water upwards. It's the formation water that we are interested in. It's not the surface water itself. And that's the philosophy behind the whole hydrogeochemistry program itself. This is an example of planning. Before we get into this, I did a comprehensive study of the faults, the fractures, the joints in the Mount ISSA region. That's because we need to know that to know how far we space it and the water connectivity between boreholes. I've worked very closely with the cartographer, where we pull out the fact mapping, from the 2011 Northeast Queensland Mineral and Energy Province report. And going through the fact maps, we start measuring or basically build up a statistics of the fault fractures and joint patterns, etc., and found that the majority of those faults and fractures are less than 5 kilometers. Therefore, if we are sort of optimistic, we use the 5 kilometers, as the sort of connectivity point. That's the result of the borehole sort of planning that we come out with. That will give a good representation of the underground sort of chemistry itself. In terms of field procedure, that's a question someone asked me yesterday. We followed the sampling methods of Ryan Noble and David Gray, and I'll give you the reference at the back of this presentation itself. The steps are pretty simple. 4-stage step. First, you locate where the borehole is. Secondly, you need to go and check that there is, in terms of contaminations, whether there's backflow, there's, streams flowing in, or etc. That's really important. And then you do the field measurement for the water table itself. That's for regional, water flow patterns to see where water comes from and where water exceeds. The next stage is sampling. If there is a bore, you take it from there's a pump, you take it from the pump. But if it's a static borehole, that has no pump, that's where, you have to do the back breaking, bailing, and, we got to, hear Dom doing lots of them, yeah. And finally, it's the field testing. There are two steps in testing. One, you do the testing on the field the moment you collected the water. The 4 things that you test for are the pH, the redox or the EH values, the temperature, and the conductivity, because this changes, with oxidation and with time. And the next thing, you collect 4 samples for lab. The first one, it's the 1.2 liter with carbon and sodium chloride, added for gold. Then you take 100 mils for alkalinity, then another 2 samples, filtered ones for cations and anions. Next, what do we talk about data? That picture is just to teach you that not all groundwater is collected, from the ground. That's Nathan Reed, climbing halfway up the windmill to collect it, in between the windmill itself. Well, all the samples are tested for 66 elements. That includes major and trace elements, and also gold and anions, as I mentioned earlier. The difference with hydrogeochemistry from conventional chemistry is they are really very low concentration. You're talking about parts per billion or parts per million, and 2 parts per million per billion. For lead, it's very high concentration. So because it's so low concentration, we need to do really very stringent QC, quality control procedures, by looking at statistics of how good it is. Like half absolute, relative deviations or standard errors, etc. The other thing is to look at the statistical appraisal. And what we did is that we look at the QQ plots to see whether, half of it, it's like, below background, or, the steps, when it's so low, you tend to get that step results due to the running up of the detection limits. All this, you could look at it individually as an elements or collectively as multi-elements. And then we generally corrected this for either half, we use half, the detection limit. The other thing that you got to calculate for every water, sample is the contamination factor, because we want to be sure that your high copper, it's natural, it's not due to contamination. And there is an equation given in the report that I won't mention it here, but that you use for that correction. And the last one, this is not used as a QA/QC, but I do include that because we calculate that for every sample, is the excess or deficit. In other words, the enrichment depletion factor relative to the water evaporation or dilution train. Basically, if you got a high sodium, it doesn't mean that it's high in sodium. It could be just, it's more concentrated than, seawater. But if you look at the depletion enrichment, you would say that, oh, that's probably, 10 times the sea level, but it's still along the trend. Or it could be, very low, but it's way above the sea level, ratio itself, based on, normally we look at 2 elements. So these are the things that you have to do before you use the data. Once you do the correction, it's smooth. It's like any geochemistry that you see, so you could play around with it, whatever you want. And in this report, we highlighted, the various ways you could use them. The first one, it's single element anomalism. Basically, if you get a high gold or high uranium, there's a high gold and high uranium, in that borehole. So that's what the single element thing does. The second one is using association, and we show examples for lithology and aquifer, in the sense that you look at either one element or multi-elements to try and decipher, in this case, lithology or aquifer, type of water, where it came from. Another way of using is that, to sort of broaden your safety net is to look at, instead of one element, you look at multi-parameters, multi-elements. So instead of looking at the elements of interest, you look at association. For example, in the first one, in the sulfur association, you try and think sort of, laterally, arsenic, moly, and tin could be associated as, chalcophilic elements. And so you throw the three together and see what sort of model fits in that association. A common method that's used in hydrogeochemistry is to look at mineral indices. That's basically knowing that, what sort of model you're looking for. For example, a VMS type, you don't look at copper only, but you could add copper to zinc, to platinum, to silver as an indices for the VMS type of deposits. Metal index, that's an index that we use a lot for this hydrogeochemistry. Again, we are testing because we are interested in copper, nickel, cobalt. So instead of just looking at single nickel or single cobalt, which generally is very low, we add nickel, cobalt, and platinum as a nickel sort of, sulfide sort of system to look for this kind of, sort of metals. And that's once that, we do, come up with results where you can look for this nickel, sort of system in Mount ISSA region. Gold association. We have few calculations for gold, but the Archean ones that we shown in the map that I'm going to show uses a combination of gold, arsenic, moly, and rubidium. We showed another one that I'm going to show is very simple, like the epithermal type gold arsenic. If you get the two, there is a sort of likelihood of an epithermal thing. And the last method you could use, instead of actual chemistry, you use a molecular, value of chemistry in terms of mineral saturations. Like the uranium, we use carnotite, basically calculated in terms of carnotite, whether it reaches the solubility product, that it's saturated or not. And you could do it for different minerals. The other uses of hydrogeochemistry is baseline. I'm not going to talk about it, is because we have a report that's been completed, and it will be appended as an appendices to this major report. Also, I've produced 38 reports to every property owners that we went to, and in that report, I spell out every borehole, every quality of every borehole, for potable water, for stock, for long-term and short-term irrigation. I think that's enough work done on that, and it doesn't interest us in this meeting itself. This is a result of what we get, from this. And one thing that's very evident is we have appended all our data to the regional pattern. That's because your data itself, it's pretty limited, and it gives you a really biased perception of, the area. But if you look at it overall as a region, you could see what's high and what's low. The first one, it's about lithologic background. We look at silica, and you find that it's really very evident that, water that's above silicate basements tends to have high silica. It's sort of common, logic there. Whereas water in the artesian basins are generally low in silica. And this is an example when I talk about, enrichment depletion factor. This is comparing sodium calcium X against Y depletion, relative to seawater itself. You find that the artesian basin, water tends to have, very similar depletion enrichment of the two elements, almost at parity with seawater, whereas water draining from the eastern Mount ISSA block generally is very depleted. For vanadium, when we look at it, we find that a strong association with the Mesozoic rocks. And being Syro, they have no idea that, Tullabag formation is one that has high uranium. And when we sort of explained it to them, they were thrilled because they could explain why it's there. The second sort of picture that we look at, again, this is single element thing, is to look at, things like fluorine, barium, sodium in a sort of our enrichment depletion curve, and tungsten. You find that, again, artesian basins is really, waters are really high in, fluorine and tungsten. But water draining, from, the Mount Isa block tends to have lower content, although we know that there is a lot of rocks that has high fluorine in there, but comparatively, it's slightly lower. For the boron sodium, you could see quite clearly that there are quite a few domains. And if you compare the domains between boron, sodium, and the tungsten one, you see very similar patterns. What we've done is that we plot the geology behind, and you could sort of explain why. It's because those domains relates to the host rock itself. Basically, it reflects aquifers from different formations itself. So that's another use. You could use that for aquifer identification. The third one is the one that I mentioned, using combining elements. Here we combine gold and arsenic together. And what it picks up, this is actual deposits that's known. Basically, the ones near the Lorena, sort of gold mines and Levuka, that trend picks up, very high gold arsenic association. And so it just shows that it is a very viable tool for exploration itself. The other ones, we talk about chalcophilic association. Here we throw in zinc, copper, and cobalt. And then, anything that highlights in it, the three of them means that it's a sulfur loving system itself. Indices are the ones that, that we use a lot, because instead of using a single element, we calculate a combination of elements. Like gold, I mentioned gold, arsenic, moly, and rubidium. And nickel, we combine nickel, cobalt, and platinum itself. And so those highs and lows and indices are not a single elements, but a multiple elements. Okay. And that's the last example. It's, where we use, canotype, for identification of uranium. It's basically looking at molar concentration of, canotype in water itself. Based on all this work, we come up with 13 areas that we have identified. And it's every area, there is a map and a report that goes, that's a map or description that goes with it, where we think what you could find in those 13 areas. So one of the results that we want, from this hydrogeochemistry is potential mineral exploration target. Next, this is the one, it's one of my sort of favorite. And so I'm excited about this, is because we are looking at the lead isotopes itself. This is a lead isotope, that's a 207 against 206. And if you understand the sort of isotopic system, this is the breakdown for uranium 235 to 207, and there's 238 to 207. I won't go into the systematic, but I will sort of, just go through the data itself. We would zoom in on that little page of data, but don't forget, we had a Queen Sally sample there, which is anomalous. For that sample, you look at it, all of them are more than 2 parts per billion. In water terms, these are high water sample, high lead samples. So we trim it down from 302 samples to 98 samples, the high lead samples, and look at the isotopic value itself. Well, this doesn't make much sense, but if you sort of put an interpretive layer on top of it, that's where, the strength of this data is. What we've done is we look at this in terms of what's known. For the Proterozoic rocks, with non-deposits, you find that this is work by Graham Carr, that the sulfur isotope do not vary very much. It generally forms really tight cluster. And for the lead-rich ones, it plots around here. And so you had Kennington, you had Dougal River that plots within that sort of, vicinity. The low lead sort of, concentration, the IOCG1 trends along that trend. Okay, so anything that plots in there, it's a possible IOCG. However, this black cluster reflects a group of water basically isolated from the lead, and it starts evolving parallel to this isochron. Means that it's dead, it has no addition, and it follows it. And so these are the ones that has probably no potential because it's just evolving there. We don't know, where it comes from. We don't know the source because we can't predict, but I estimate it to be about 700 to 800 million years in a sort of, event, or associated rocks of that event, or suppression of, from 7 to 800 million years and evolve along the isochronism. Now we look at the other elements that spread along there. The greens are samples that's probably within this group of dead lead isotope, but it's been mixed with that evolution line, the lead evolution line, and moves outside of that. The blue dotted lines are the lead lines for the Western Fault Belt, and the purple ones is the Eastern Fault Belt. So that's a lead evolution line in that area. The reds, the blues, and the orange are generally sort of high potential. And when we read these high lead samples for potential links to Proterozoic rocks, I'll show you what it means later on. The blue ones here are initially I thought it's dodgy, but then with further discussion, it could be a mixing between the dead group of dead water and the isotopic water from the IOCG, and so it's included into that. While plotting all those things that we've identified into highly likely Proterozoic to low Proterozoic likelihood, we come up with this, our 4 trends. Basically, for once that's Kennington that we knew, because we're mining from lead from a Proterozoic rocks, it has to show up because it's nothing. So what's the use of this data? Well, the use of this data is that for undercover, you want to find where Proterozoic lead, high Proterozoic lead water comes from. If it's, it's Proterozoic, it has to be Proterozoic. But if it's undercover, you don't know where it is, and it's popping up, telling you there's more Proterozoic lead there. And we find the trend goes south to Tullabag. And that's really interesting because South 32, I think it's down there looking already. The second trend is from, El Luis, Altia, and it goes further north to Levuka, undercover as well. And we know that trend, it's a high potential, that goes further north to Levuka, sort of, homestead. The third trend, it's the one that I think, and I put, if I'm a sort of, betting man, I'll put my money on this. You had a trend that goes from Cloncurry through Ernest Henry to 3 boreholes. And I'm talking about 3 high lead boreholes just south of Kelowna. And from my years of, experience, as a geochemist, I think this is a good indication. If you are looking for the next Ernest Henry, or probably bigger than the next Ernest Henry, this is the area that you need to look for. So I'm confident that there would be an Ernest Henry in that area. Okay. And the last one, that train is, I call it the Roseby corridor train. It's within the Mary Kay. It sort of picks up all the, the deposits that, Roland and all of them talk about, from Hillview, to Little Eva, Dougal River, and all up to as far as I think Queen Sally. All of these are deposits in Proterozoic rock, and so there is no surprise for them. But the 2 things that's interesting is the one near Kelowna and the one near Levuka. To conclude, hydrogeochemistry, it's a powerful exploration tool for blind and concealed deposits. Blind and concealed undercover because you want to look for Proterozoic signals undercover. It is very different from conventional chemistry. And so you can't just get a chemistry, get the data, plot it, doesn't work, walk away. No, you need to do the processing before you could use it. You have to plan it. It's not good just going there and pick any samples without planning because you may get false negative because you missed that. Okay. And lastly, from this program, we have found 17 potential areas or trends that will have implications for future exploration. There are 2 reports. The first is the environmental report, which has been completed and it's added as an appendix. But it's a second report, the major reports, that I'm a bit disappointed. The reason for that is that it's supposed to be released already, but on the day before we release, a collaborator found out that they did a wrong correction factor for the lead isotope. So we got to go back and change everything, reassess everything, replot everything. And so I have to go back and rewrite the sections again. And so as a result of that, I will try my best to release it earliest possible next year. Thank you.
Thank you, Joe. You went way over time, but I knew you were very excited about that, so I'll let you go. So is there any questions?
Thanks, Joe. That was really good. I have two questions, actually, probably quick ones.
Yep.
First, do you have any information on the direction of flow of water?
We had the only direction we had is the flow pattern of artesian, the Great Artesian basins from east to west. And anything nearer, you need to do basically localize water level monitoring to see where trend flows. Other than that, we don't.
So the next question would be some of the drill holes through the cover, the intersecting veins of lead and zinc and so on. So what is the likelihood of actually some of these signals coming from this type of mineralization in the cover rather than in the basement?
Well, the choice of boreholes that we sort of pick are ones that's within cover sequence. We avoid ones that's actually penetrating right to the basement rock itself. So we are trying to avoid that. But in the western side, where you had a lot of this Rossby corridor, some of them could have done that. And definitely for these purposes, the isotopic purposes, we know it's Proterozoic, so we are less concerned about that. But then, it's the mineral, indices that, probably tell that there is something, like we said, the events characteristic of that day.
Thank you.
Thank you.